Okay, so we are looking at FOL, and in particular we are looking at reasoning aspect. We shall not have the time to look into the knowledge representation aspect too much here. So, we will assume some simple representation schemas, which means the choice of the functions that we are talking about, the set of predicates, the set of functions and the set of these things. Now, we saw two rules of inference. One was universal instantiation, which said that from for all x, I mean this is an instance of that, you can infer P of A, and then we saw generalization, which says that from P of A you can deduce there exists x P x. So, in case you have a query of this kind, we saw an example of that earlier. Now, in addition to this, there are also some rules of substitution. So, for example, you can replace for all x P x with there exists x not P x, and likewise there exists not exists x P x is equivalent to for all x not P x. So, these are kind of common sense rules. So, if you see what we are saying here, we are saying that if it is not the case that for every x some property P or some predicate P is true, it means there must be some x for which P x is not true essentially. So, if you move the not across a quantifier, it changes the nature of the quantifier. If you move a not across a universal quantifier, it becomes an existential quantifier. The rest of the expression does not change. It is like you are moving the not inside, but changing this. Likewise, if you change the move a not across the existential quantifier, it becomes a universal quantifier. So, again if you look at this, this is like saying that for example, if P x stood for something which is both even and odd. So, this left side is saying that there does not exist an x which is both even and odd, which is equivalent to saying that for all x it is the case that they are not even and odd essentially. So, you can move them across on both sides. So, these are rules of substitutions which are quite useful in some situations. We will see some of them, and you might be familiar with them. They are known as De Morgan's laws. Also, some things which are used sometimes is that, for example, if we have for all x for all by P x y, where P is some predicate, this is equivalent to for all by for all x P x y. So, the quantifier of the same kind you can interchange without changing the meaning of the sentence essentially. Likewise, for there exists y, there exists y, there exists x, they would be similar, but if the quantifiers are of different kind, then you cannot do that. So, if you say for all x there exists a y such that P x y, this is not equivalent to saying that there exists a y such that for all x P x y. So, you can try and think of a counter example to show that this is not the case. So, for example, for every number x, there exists a number y which is bigger than x. So, if P stands for bigger than or greater than, then this statement is true, whereas this statement says that there exists a y which is greater than every number. So, which is obviously not true essentially. So, you cannot switch two quantifiers of different kind, if you do switch them, the meaning changes, the truth value also will change, and you are talking about something totally different here and something totally different here. Whereas, here there is no difference, if they are of the same kind, then you can switch the quantifiers and it does not change the meaning. Here we are saying that if you have a negation sign, you can move it inside inwards towards the expression, and what it does is it changes the sign of the quantifier, changes the nature of the quantifier. Universal quantifier becomes existential and existential becomes universal essentially. Which is why I had mentioned in the last class that it is not very easy to identify what is really the nature of a quantifier. So, for example, if I make a statement, it does not let us say we are talking about people, and this statement is saying that there does not exist an x who is divine essentially. What is the nature of this variable x? Is it a existential variable or is it a universal variable? And this becomes important, because if you remember the implicit quantifier form that we discussed in the last class, you can replace a universally quantified variable with a question mark and then it becomes implicit. So, is this a universally quantified variable or an existentially quantified variable? So, the way to look, your answer is right. The way to understand that is to push the negation sign as much inside as possible and then look at what is the outermost quantifier essentially. So, if you push the negation sign inside, it would become equivalent to saying that for all x not divine x. So, we are saying that everyone is not divine, which is like saying that no one is divine essentially. So, this is a universally quantified variable. So, we can replace it if you want to put it in implicit quantifier form by saying not divine x by putting a question mark. That is a convention we are adopting between ourselves, so that we do not have to write the quantifier, we do not have to process the quantifier when we are writing a program to do that. We can just treat those kind of variables as universal variables. So, just a word about what do you do with existentially quantified variables when you are talking about implicit quantifier form. Let us look at a sentence like this: there exists x even x. So, it is saying that there exists some number which is an even number essentially. The way to convert this into implicit quantifier form, and the process is called Skolemization. After a logician called Skolem, Thoralf Skolem, who first introduced these ideas, by replacing it with a constant, even SK12. So, conventionally we may say we use a name SK. This is just again between us, it does not impact the meaning of what we are writing. It is a constant. So, what have we done? We have removed the quantifier and replace x with something called SK12. So, SK again is just in honor of Skolem. You could have used any constant, as far as you remember that it is a constant which has been introduced in this process, and it must not be a constant which is being used anywhere else. So, you cannot say for example 0 if it is a constant or something like that. You must use some unnamed, some new name and treat it as a constant after that essentially. Because if you look at the meaning of the statement, it says there is some number which is even, and all you are saying is here that there is some number which I am calling SK12 and that is even essentially. Of course, you may not really know what that number is, but you can do that essentially. If you have something like this, a statement like this, for all x there exists y p x y, then if you look at the what is this sentence saying? This sentence is saying you should always read the quantifiers from left to right, that for every x there exists a y such that p x y is true essentially. So, for example, for every x there exists a y which is greater than x essentially. So, that is an example that we mentioned in the last class. We can transform this into an implicit quantifier form by writing it as p x xp11 x. So, what are we saying here? We have, when we have a existentially quantified variable inside the scope of a universally quantified variable, then we are replacing that variable with a function of the other variable, and the function is a Skolem function. So, this is a Skolem constant of x. So, what is this function? We do not know what that function is. It is some function, and what we intend by the usage of the word function here is that the value that the variable can take is dependent upon the value that x can take essentially. So, again if p stands for greater than and the implication and the meaning of this is that y is greater than x, because the meaning is always determined by us, it depends upon the relation that you are talking about essentially. Then what we are saying is that for every x you can choose a y such that y is greater than x. So, that y that you choose depends upon x, and therefore, we can think of it as a function of x. We do not know what that function is, but it is some function. As far as reasoning is concerned, we will treat it as a function and translate this into this statement. So, in general, of course, if you have for all x1, for all x2, for all xn, p x1, x2, y, then we will translate it to p of x1. So, I should put a question mark here, okay, because x is a universally quantified variable, x1 So, this y which is in the scope, so there exists a y here, is in the scope of all these universal quantifiers for x1 to xn. So, this y becomes a Skolem function of x1 to xn. So, in general you just look at what are the quantifiers on this side, universal quantifiers on this side, and make that variable a function of that essentially. If I had something like this, there exists x for all y p y p x y, then I would replace it with p s k 5 y. So, this entire process of converting a sentence into implicit quantifier form, nowadays we call it as Skolemization, after this logician Skolem essentially. Okay. So, in the last class we had started looking at forward chaining, we had looked at the rule of modified modus ponens, which said that if you have alpha prime and alpha implies beta, then you can produce beta prime from there. And if you move from alpha prime to beta prime, the process is called forward chaining. So, in forward chaining, you have alpha prime and then you can add beta prime. In backward chaining, you want to show beta prime. So, we use this convention show beta prime. So, we have a sub goal now, show alpha prime. So, backward chaining, we just started looking at it in the last class. It works with goals. By goals we mean something that we want to show to be true, a formula that we want to show to be true, and looks for implications of this kind, alpha implies beta. So, basically it is using modus ponens in a slightly different form, or if you think a little bit about this, you can see that what backward chaining is doing is this kind of modus tollens. Maybe that will become clearer as we move forward. That is a different rule of inference. So, if we have our original Socratic argument which said that man x implies mortal x, and in our database, so this is there in the database and this is there in the database, which is man Socrates and of course, we may have other data, but let us ignore that for the moment, and you wanted to show that mortal Socrates is true, then forward chaining would apply this modified modus ponens rules and in this form and this form, this thing, whereas backward chaining we have not written it in this form, but it says that with show beta prime and with alpha implies beta, you can reduce it to show alpha prime essentially. So, show mortal Socrates. How does this work? So, if you recall, we match this with a unifier x is equal to Socrates. We will look at unification a little later. So, we apply this unifier to this, and according to this backward chaining process, we reduce this to show man Socrates. So, let us put goals inside boxes, so that we can distinguish between goals and facts. So, this is a fact, this is a fact, this is a goal, this is a goal, and so on. So, what this, of course, the trivial way to simplify to solve a goal is to see whether it is present in the database. So, in this example, when we have this goal of show that man Socrates is true, then you simply look up the database and you find that it is true essentially. In a moment we will look at how the language prologue is basically doing this essentially, which is it is doing backward chaining, and if a fact is present in the database or in your program prologue program, it is trivially true essentially. But the nice thing about reasoning with logic is that we can ask a question like, is this formula true? that does there exist a y such that mortal y is true. This is what is given to us. This is a database and this is a database. Given this database, is that statement true that there exists a y such that mortal y is true. So, I have intentionally used a different variable here y and here and x here. It is not really necessary for me to do that, because when you look at this statement, then it is saying that for there exists some y such that that y is mortal. I could have jolly well said there exists some x such that x is mortal, but because we want to sort of keep our formulas clean and apart, and it is a practice that is necessary, as we will see, we use a different variable name, which is a goal. Now, if this is my goal, let us show that this is the case, then we invert the Skolemization convention. When we are doing forward chaining, a formula like this, a formula which has a universally quantified variable is put with a question mark here, whereas in backward chaining an existential variable is denoted by a question mark. That is specifically in backward chaining. When you are talking about when you are talking about goals, for goals the convention is reversed essentially. So, I will treat this as mortal y. So, again let me emphasize that when I write show mortal y in this form, this notation denotes an existentially quantified variable. That is true only for variables which occur inside goals. So, inside goals the convention is reversed essentially. In the next class we will see why that makes sense, but you can try and guess. So, I can ask a query, existential query. So, this is now becoming like a little bit like a database essentially activity. So, you have some set of facts available to you and you are asking a query, is there some entity which satisfies certain properties. So, if you are saying something like is there an employee who earns more than 10,000 rupees and something, and you get some results out of that essentially. Okay. The difference between something like RDBMS and using logic is that logic can make inferences on the way essentially to retrieve answers for you. So, when you are asking a question that is there somebody who is mortal in the knowledge base or database, whatever you want to call it, the knowledge base has only two statements in our small knowledge base, that Socrates is a man and that all men are mortal. The knowledge base does not say that anyone is mortal, any specific individual is mortal, but backward chaining in particular and reasoning in logic in general allow you to ask existential queries like this and answer those queries after a process of doing some inferences, making some deduction essentially. So, what do? We match this show mortal x with the right hand side of our statement implication mortal x. So, we say x equal to y is the substitution you want. So, this becomes mortal y. So, this gets translated to show man y. So, our query about, so it is still an existential query, it is saying is there someone who is mortal, gets translated into a sub query or a sub goal which is there someone who is a man essentially. Now, that can be trivially answered by the database, yes Socrates is a man. So, we can terminate the query and return the answer to this query by saying yes y equal to Socrates is the answer to your question essentially. Okay, so, in the last class we had briefly mentioned that you could define. So, let us say you want to define grandfather or let us say you want to define grandparent. So, you might want a statement like this, for all x for all y so let us say GM stands for grandma x y, and let us say this means that x is the grandmother of y, implies let us say GP stands for grandparent. Let us say for some reason we want to put this rule into our knowledge base or database, what you want to call it. So, what you are saying here is that grandmothers are grandparents. Then you could have a rule like for all x for all y GF and the same thing. Then you could have a rule which says for all x for all y and for all z mother x y and father z x implies grandfather z y. I could have a rule of this kind which says that for all x for all y for all z, if x is the mother of y and z is the father of x, then z is the grandfather of y essentially. So, you could imagine that you are building a database of relationships where you are defining what each relationship means, what is a grandfather, what is a grandmother, what is a grandparent, and so on and so forth. And then you should be able to ask a query. You should give us database of facts. So, let us say the basic database only contains the mother child or let us say parent child and the gender of each person essentially. So, I could say Jane is the parent of Tom and Jane is female and Tom is male. So, I could have this kind of database. So, there is only one relation, parent child relationship and gender relationship. Then you can define a mother as saying that x is the mother of y if x is a parent of y and x is female essentially. So, you could do all that kind of stuff, we will not get into the details, but you could have a knowledge base of this kind and then you could ask a question, how is Peter related to John for example, then the system should try to find out whether what is the relation between them. Of course, you cannot ask this very generic question as to how it is related, you can ask something like who is John's paternal uncle for example, you could ask such questions essentially. Let us say we are interested in talking about grandparents, whose grandparent, and that is our basic query about. Then you can see that grandparent x y can be solved in two ways, that either you are a x is the grandfather of y or x is the grandmother of y. Then you could say x is the grandfather of y if you could use this as one rule which says that, now you have to be a bit careful here, father x z. So, I am just using different names just to be consistent here, and mother z y. And you can imagine that there is another rule which uses father and father in both the places. So, that is two possibilities here. So, you can see what is happening here, that the space in which backward chaining operates, if you ask a query about something, is John the grandfather of Peter, then this system will try to apply. So, in backward chaining you match with the right hand side of an implication and see if the left hand side can become a sub goal. Now, you can match either with grandparent. So, you can match either with this rule or with this rule. In both cases grandparent will match. So, you could either use R1 or R2 if you call it. One rule will take you here, another rule will take you to grandmother. So, either x is the grandfather of y or x is the grandmother of y. Then grandfather, if x is the grandfather of y, it could be that x is the father of z who is the mother of y, or it could be that x is the father of z who is the father of y, both are possible. So, you have all these different possibilities, and the space that backward chaining will have to search is that is an AND OR tree essentially. And what Prolog does is essentially it does depth first search on that tree. So, let me rewrite this here. Okay, I am skipping the step of Skolemization, which in this case is simple because we have only universally quantified variables. So, you can just replace everything with a question mark before that. If you were to write this in Prolog, you would write it as something like this GP. So, Prolog uses a different convention. See, we are using a convention that question mark stands for a variable and something without a question mark stands for a constant. It could be a constant or existentially quantified variable which is a Skolem constant or something like that, it does not matter, but that is a convention we are using. Prolog uses a different convention. Prolog uses a case that when you have x and y uppercase letters, then it is a variable essentially. So, those of you who have used Prolog would know this. So, let us stick to our convention, which is to use a question mark. So, we write the consequent first and then we write the antecedent. So, this same rule, let us write it like this. So, what has happened? I have taken this rule and rewritten it like this. I have thrown away the quantifiers, I have converted it to an implicit quantifier form, and I have inverted the order in which you are writing. In a normal rule, you write the antecedents on the left hand side and the consequent on the right hand side. In this notation, I am writing the consequent on the left hand side and the antecedent on the right hand side, and I have changed the direction of that. So, I have used an arrow instead of that sign here essentially. So, again those of you who use Prolog would know that Prolog uses something like this instead of the arrow sign, but it means the same thing, that is only a matter of convention essentially. This is easier for us to understand that the direction of implication is from right to left essentially. Then I would write the second statement as GP x y GM x y, then GF x y, then somewhere I would write a statement for GM, then GF, which is what I have written here, which is that GM x y if mother x y. Prolog uses a comma instead of and, so we will also use a comma here. So, keep in mind that this comma basically stands for an and. So, the same set of statements we are just writing in a different syntax, we are not changing anything, we are converting it into implicit quantifier form and we are writing it consequent on the left hand side and antecedent on the right hand side, and we are replacing ands by commas and this kind of stuff, but the statements are still the same, they are still the same universally quantified statements in logic essentially. Somewhere down there I would have, let us say mother Jane Peter, sorry,
It should be Z.
oh yeah, X is the grandfather of Y, so Y is the mother of, no sorry, Z is the mother of Y and X is the grandfather of, X is the father of Z. Okay, thanks. Somewhere I would have a statement saying mother Jane Peter, for example, and father Peter John, and maybe other facts also. So, you would recognize this as a Prolog program, I hope. A Prolog program is statements of these kinds. Now, this is a restricted form of logic, but we do not go into that. The restriction here is that the consequent can only be one predicate essentially, you can't have more than, you can't have ors inside here and so on and so forth. But you can recognize this as a Prolog program. What does Prolog do? If I ask a query like, is there or show grandparent X. So, let us say Peter Z or something like that. The reason for writing things in this inverted form is because it makes the task of matching simpler. You always match with what is on the left hand side in your program, and the right hand side is the step of making that inference. So, if I ask a query like that, is there someone who is Peter's grandson, or is there someone, to be more precise, whose grandfather is Peter, then Prolog starts looking from top to down, trying to match this with the things on the left hand side. In this example, very conveniently it matches the first element itself. So, when it matches this, it poses this as a goal essentially. So, it will ask whether Peter is the grandmother of some Z essentially. So, it will translate that goal into the sub goal. So, backward chaining we said was moving from right to left in this notation. So, in this notation it is moving from left to right. So, it basically goes from goal to sub goal, asks that as a new query, and as you can imagine, I should have something like, okay, I have I could use parent here and then female Jane and so on and so forth. I mean, that is a data that I originally said we have, that Jane is female, Peter is male and John is male and that kind of stuff. This will get translated to GM grandmother Peter Z, which in turn will, so essentially you are going down. Okay. So, because I have written this rule first, this grandmother rule first, it is like having this rule on this side. So, it is going down that path essentially. So, you can visualize what Prolog is doing as backward chaining and with a particular strategy, which is depth first search, and the way it is implemented here is that the first rule which matches, it tries that essentially. So, it tries this. So, just imagine that that tree was flipped from left to right. So, it would be going down the left side first, and then it would eventually not be able to show that Peter is a grandmother of Z. It would backtrack and then try this second rule essentially, which amounts to saying you go all the way down and then try the other branch essentially, exactly as we had done when we looked at goal trees with depth first search first essentially. So, let us look at another example that we have considered earlier, which is that of planning and outing. So, if you recall when we were looking at goal trees, we had this task of planning and outing with a friend, and the outing consisted of some 3 things, that one evening out, one entertainment, and followed by dinner essentially. So, eventually you have to find values for these which your friend would be happy with essentially. So, if you remember, it was something like this, that let us say let us call it a birthday plan. I do not remember what we had said that time. So, you have a birthday plan made up of x, y and z. If you have an outing plan of called x and an entertainment plan called y and a dinner plan called z, and then you could say an outing plan is a valid plan if it is an outing and likes let us say F stands for friend X. Likewise, other 2 plans, entertainment plan and a dinner plan essentially. So, you could write it as a Prolog program. You could say that this is how. So, you could add F as a parameter. So, x comma f here comma f here comma f here. So, let us say f is your it stands for your friend, and let us say your query is essentially that. So, let me write the query here. What is a good birthday plan x, y, z, and let us say the friend's name is Peter, and this is my query. So, let us put a question mark after this. What backward chaining will do is exactly the same thing that we did here earlier. It would, so this is birthday plan, then it tries to find an outing and entertainment and dinner, or maybe instead of entertainment we had said movie in the last class, so it does not matter. And below this would be an OR tree which said that outing, let us say beach or mall and things like that, and entertainment could be some movie A or movie B or movie C, and restaurant could be some restaurant D or E or F, and below that of course you have the facts like whether your friend F likes going to the beach. So, some statement like beach Peter, it must be present in your knowledge base, because that is how you will, instead of asking a friend, you are saying that is there a statement like that in my database already essentially. So, the attention that I want to draw to you here is to the same problem that we encountered. Now, you must try and recall what was happening there. You are searching this AND OR tree, and well, initially we had posed it as a simple OR tree essentially, but what we were saying is that let us say that you decide that you want to go to a go to the beach, you ask your friend shall we go to the beach, and then you are doing a depth first search. So, you try all these options one by one, you say shall we go to this movie A or shall we go to this movie B or shall we go to this movie C, and then try all combinations of this. So, for example, beach and A and D, then beach and A and E, then beach and A and F, and let us say all these fail essentially. So, what is happening here in backward chaining is that you are doing this sub goal formulation, and okay. So, the way Prolog does is that it goes from top to down and left to right. So, given 3 sub goals outing and entertainment and dinner, it will first try outing, try to find a value for that, let us say beach, then entertainment, and then try to find a value for that, let us say A, and then dinner and try to find a value for that D, and at that point let us say it fails and say that no, this is not a good birthday plan. So, it will backtrack and try E here. So, it will still be in this goal, but it would try a different value. So, whenever backtracking happens, it happens in these same directions. So, when it is backtracking here, it goes up one step, when it is backtracking here, it goes up, when it is backtracking here, it goes down one step, when it is backtracking here, it comes left one step. So, it tries the first option for dinner, the second option for dinner, and the third option for dinner, and everything fails. You do not want to repeat this same search again for a different option of B, if you can figure out somehow that beach is a culprit. So, we had mentioned the term dependency directed backtracking there. So, in some systems like in constraint satisfaction systems, that is kind of done automatically, the system keeps track of what is a dependency, but in a system like this, in logic or an implementation of logic called Prolog, the language gives the user the ability to control backtracking. So, instead of writing a statement like this, what you can do in Prolog is to, instead of this, you write the statement as follows, that a birthday plan. So, let me just use this B x y z f. If outing plan, then you use a special symbol called cut, then an entertainment plan, then you use a special symbol called cut, and then a dinner plan. So, instead of 3 sub goals, you have added 2 extra sub goals. These are very special sub goals which Prolog allows you, and so those of you who have used it would know that this is a cut operator as it is called, and what it does is that it is basically a device given to the user or the programmer, if you want to say, to control backtracking essentially. And what it is basically saying is that if you are going to backtrack from this to this side, then do not try a new value for this, really jump back to the original goal essentially. Anyway, without going into the details, I just want to point out that the cut feature of Prolog is basically used to control this huge amount of backtracking that one ends up doing in an unconstrained search essentially. Okay. So, what Prolog does or what backward chaining allows you to do is to allows you to ask existential queries. You can ask some query about, is Peter the grandfather of somebody, or who is John's grandfather, or you could define, and maybe that is a good exercise for you to define the ancestor of. So, when is an X an ancestor of Y, then you could ask a query whether John is an ancestor of someone or things like that, and the system will search in your database. It will make inferences by jumping across such implication signs and eventually dig out an answer for you essentially. This process is often called as deductive retrieval. Which is more than what a database system gives you. Database system gives you retrieval in an efficient fashion, but it does not do deductions on the way essentially. Prolog allows you to do deductive retrieval, and in that sense it is more powerful than an RDBMS system. And in fact, Prolog is a complete programming language. Anything you can do in Java, for example, you can do in Prolog essentially. And logic programming in general is also a complete programming paradigm essentially. But it has its limitations essentially. So, I had hinted about that when I said that there is only a limitation in the format in which you can write Prolog programs. It works with only a subset of logical statements which are known as horn clauses, which basically say that there can be only one consequent in any implication statement essentially. So, it is not complete. I refer you back to this problem of 3 blocks that we had mentioned in the last class. We had said that A is on B and B is on C, and A is green and C is not green, and we had said that is it true or does there exist 2 blocks X and Y such that X is on Y and X is green and Y is not green. We cannot solve that problem using either forward chaining or backward chaining. So, in that sense forward and backward chaining are not complete, and remember that when we talk about logical systems we are interested in sound and complete systems. Everything that we are doing here is sound because it is based on sound rules of inference. It is only the completeness which is in question essentially. So, in the next class, which is the last class of our course, we will look at this use of resolution method which we saw for propositional logic and apply it to first order logic, and see that that particular problem which I will discuss again in the next class can be solved using resolution method essentially. Okay. So, on the way we will need to just have a quick look at the unification algorithm, which is this algorithm which is used for matching 2 terms like this essentially, which is necessary in the implicit quantifier form that we are using here essentially. So, I will stop here and we will meet in the next class for the last time in this course.